Hello, in this video I'm going to talk about Kepler's laws of planetary motion. So these are three laws that Johannes Kepler developed in the early 17th century that describe how planets orbit around the sun. I mean, in fact, you can apply these laws more widely than that to any small object that's orbiting something a lot bigger. So that's in relative size when I'm talking about small objects. So, planets aren't small, but they're small in comparison to the sun. So we can apply Kepler's laws to moons that are orbiting big planets or satellites that are orbiting the Earth. So they do have wider application than just planetary motion. Now, we're going back to pre-Isaac Newton here. This is early 17th century. Kepler published the first two of the three laws in 1609, the third one in 1619. So this is 50 odd years before Newton wrote the Principia. This is before we had Newton's laws of motion. It's before we had Newton's universal gravitation. So Kepler was having to work out these laws and discover these laws based off of observational data. And he was analysing a lot of observational data that either he collected himself or had been collected by other astronomers, most notably Tycho Brahe, the 16th century Danish astronomer, who was known for very accurate astronomical observations, at least for the time. So Kepler analysed these, he came up with his laws, and then subsequently they fed into Newton's ideas and the work that he was doing to develop the Principia, along with the work of Galileo and people like that. So let's get on to what these laws are. And the first law is saying that the orbit of a planet is an ellipse with the sun at one focus. So let's remind ourselves about ellipses. So these are ovals. So I'll draw an oval out, and you might remember drawing these when you're at primary school, actually. And you get a bit of wood, you bang a couple of nails into the bit of wood, and then you put a string, a slack string tied to each nail, put your pencil inside the string to make the string taut, and then see what shape the pencil will draw out while you keep the string taut. What is the envelope that you draw? And you end up drawing an ellipse. So you've got an ellipse here with two focuses, which is where you've banged in the two nails. And what Kepler's first law is saying is this is the shape of the orbit of a planet around the sun, and the sun is at the location of one of those nails. Now, planetary orbits aren't as elliptical as this. They don't have what's called highly eccentric orbits. The eccentricity of an ellipse is describing how much wider it is in one direction compared to the other. You've got a major and a minor axis, and the eccentricity is talking about the ratio between those lengths. Now, most orbits are pretty close to being circles. I mean, even the most eccentric ones aren't that elliptical, but they are ellipses nonetheless. Let's look at the Earth. If you're going from closest approach, so here's a bit of terminology. So closest approach, say the sun was at this focus. So when the Earth is here at closest approach to the sun, that is referred to as perihelion. So this is from the Greek. You've got peri meaning near, helion referring to the sun, so nearest to the sun. So that's our closest approach. So when we're at perihelion, you're looking at 147 million kilometers. When we're at our furthest from the sun, and people disagree on pronunciation of this, I prefer aphelion to stress the two parts of the word. So ap meaning furthest, far away, away from. So aphelion, away from the sun. Some people soften the ph and say aphelion, but I'm not as keen on that. Sounds a bit Shakespearean to me. So, but anyway, when we're at aphelion, we're then at 152 million kilometers. So that's only about a 3% difference. That's pretty low eccentricity. Venus is even more circular in its orbit. So, okay, Mars and Mercury have got a bit more eccentricity, but these are fairly close to being circles. So that's the first law. Second law. This is about the area swept out by a planet in a certain amount of time in its orbit. So let's draw out our exaggerated orbit again and put the sun at one focus. Say, right then, we've got a planet here and it moves to there in certain time, say t. So what area has it swept out in the orbit? Draw out lines from the sun. That's the area that it is swept out. It's an area inside the orbit that has been swept out in time t. Let's take another point in the orbit. So here, and in time t, it would have travelled further this time because it's sweeping out the same area. So if I then shade in this bit, these two blue shaded regions have got the same area. So when the planet is closer to the sun, it's travelling faster because it needs to sweep out the same area. Now that fits in with what we know about conservation of energy, because when the planet is closer to the sun, it's got less gravitational potential energy, and that has been transferred into kinetic energy. So it's moving faster, so it can sweep out the same area inside its orbit. So close to the sun, moving quicker, further away from the sun, moving slower. If you were going to do a proof of this, I'm not going to do it here because it's pushing the limits of our pre-university maths. You'd have to be doing, if you're doing further maths, you'd be fine because we'd be looking at the vector product, the cross product. But the easiest proof to do of this is looking at conservation of angular momentum. And then it drops out quite quickly that this is going to be the relationship between these areas that are being swept out. So that would be your go-to, conservation of angular momentum. And in Kepler, historically speaking, he came across this in a bit of a weird way because he was doing his analysis off of a lot of Aristotelian assumptions. So the assumptions that Aristotle was making, over a thousand years, nearly 2,000 years before this. And a lot of those assumptions were just wrong, really. We've discovered that these were not correct assumptions. But Kepler's analysis still came up with a correct conclusion to what was actually happening in terms of sweeping out these areas. So even though he was putting wrong assumptions in, he got a good answer coming out the bottom of it, which is a little bit strange, but there you go. So that's the second law. Let's go to third law, the last one of the three. And this is giving us a relationship between the orbital period and the average distance from the sun, saying that the square of the orbital period of a planet is proportional to the cube of the average distance of the planet from the sun. So how accurate is this? I mean, again, it's an approximation. These are all approximations to a greater or lesser extent. This one, I mean, it's not bad. I mean, there's a lot of things which perturb these and make them less accurate than they could be. So first of all, we've got the mass of the planet. If you're thinking about the first law, the sun isn't sitting unmoved at the focus of the ellipse. It's also orbiting around the center of mass of the system. You've got mass in the planet that's orbiting the sun, and it is moving the location of the sun. So the first law is an approximation from that point of view, that the sun does move a little bit. And of course, it's being pulled by 8 planets plus everything else in the solar system. So it's got a wobbly motion around the point of the focus of the ellipse. So that's one approximation that we've got kicking into this. You've also got the effect of all of these other planets, particularly Jupiter, with the amount of mass that Jupiter has got. And Jupiter is perturbing the orbits of all of the other planets, as are all of the other planets on each other. So you've got variability related to that. So that's going to throw in more uncertainty into these calculations and these laws. You've also got, particularly for Mercury, because it's close enough to the concentration of mass in the solar system, i.e. is close enough to the sun, that you start getting the breakdown of classical mechanics, and you have to describe the orbit of Mercury using general relativity. Obviously, I'm not going to do that here, but that would be another reason for error coming into these laws. So with all that in mind, we're not going to get an exact relationship. You can't say exactly for every planet the square of the orbital period is going to be exactly proportional to the cube of the average distance from the sun. I mean, if we compare these for some of the planets, so you can normalize this for the Earth. So if you take t squared over r cubed, so that's going to be equal to the constant of proportionality in this. Well, if we do this in Earth years squared divided by astronomical units cubed, so that's normalizing it to 1 for the Earth, because you're going to have 1 year squared divided by 1 astronomical unit cubed, which gives 1 for the Earth. So we've normalized it to the parameters for the Earth. If you then use these units, Earth years and astronomical units, you'll get about 0.9 for Mercury, 1.1 for Venus. So you're getting these 10% variations in this relationship, which is still pretty good when you consider how much is actually going on with all of the perturbations in the orbits. We can, subsequently, since Newton, and seeing that these orbits are nearly circular, they don't have high eccentricity, we can do a simple circular motion analysis on this. So we could do our mv squared over r is equal to gmm over r squared. So just doing our Newton's law with our centripetal force equation, so Newton's second law with Newton's law of gravitation, we can then, so that's going to give us, well, we can cancel that and that, cancel some r's. So we've got v squared is gm over r. We also know that v, because we're talking about the speed of the planet in its orbit, well, if we're saying it's a circle, then we can do 2 pi r over t. That's just our distance over time is our velocity of a planet going around a circular orbit. So we're going to end up with 4 pi squared r squared over t squared for our v squared is going to be equal to gm over r. So you can see where this is going. We then get t squared as the subject is going to be equal to r cubed. There you go. That's our proportionality. And then the constant is 4 pi squared over gm. So doing a bit of circular motion analysis gives us this. But yeah, these are approximations for all the reasons that I've already given. So yeah, they're interesting, these laws, that they're powerful for describing how things are orbiting. They're very interesting historically, of how Kepler managed to pull these things out from observational data before Newton. And this is no mean feat. I mean, I know there's some reservations about how he came up with the second law, but it's still an astonishing piece of science. And yeah, we can still apply these things nowadays. These are still, these eccentricities, these orbital periods and these distances are still things that we talk about in terms of the motion of planets and moons and satellites and things. So yeah, these are still applicable today. So there you go, Kepler's laws of planetary motion.